decades, obviously. And the new division, Starline DC Solutions, is what Dave and I have started up with Universal Electric. And the DC stands for direct current, not data center. So it's applied in data centers using direct current. So 380 volts DC for data centers. This is an update, and the point is it's more than just efficiency. But before I get started, how many people have been following the 380 volt DC initiative? Got a couple here. Okay, a lot of controversy. We're getting a lot of attention from AC folks. It's basically it's the Edison Westinghouse discussions all over again. Thomas Edison, great inventor of our time. Basically, how many have read Empires of Light? Couple? Not many. Got to work on that. This is a very well-written story of the AC-DC battles, back when Westinghouse was raising the issue of safety, going out and electrocuting elephants and dogs and all kinds of terrible things. It was amazing what took place back in those times. We've read the book several times. Dave's been giving it out for a while. There's a couple lessons learned that we're trying to keep this initiative going. Lessons learned? It's about the return on investment, stupid. In the book, it documents the World Fair battle. In other words, Westinghouse and Edison fighting for the order to electrify, to light up the World's Fair in Chicago. Westinghouse won. He won because it was the lowest price. Okay? There's a return on investment. So we can talk about all these other things about why use DC, but until the return on investment is solid, then it's not going to happen. I think we'll make a compelling case today. About safety, AC and DC is electricity, and both can be dangerous, but both can be made safe to use. We're not going to say we're safer or not as safe. Vice versa, we use many of the same components by rated manufacturers, standard UL listed products. Both organizations, both the AC and DC, should strive to make it safer always, and we certainly have that in our business model to do that. And also, never give up. Good ideas aren't solved right away. Edison said on the previous slide, try again when you think you're ready to quit. And so that's the point. Take a moment and read this. To me, this was very compelling. And for those in the back that can't read it, I'll help you out. It basically says 80% of the power in commercial buildings today has to be converted to DC to be used. It's already a DC world. It's hidden. It's all around us. Everything in this room needs DC in one form or another to work. And in our humble opinion, AC power for data centers is ready to flatline. A little play on words, pardon the humor. No, it's not going to happen overnight. But the flat line is the DC straight curve, is what we're talking about. And we'll see if we can't cover the whys. But let's look at some trends. We know that the world market, energy consumption, is going up. While it's going up, we also need to keep an eye on all of the energy concepts, not just electricity, because they're becoming interrelated. The transportation industry with electric vehicles is starting to compete for those electrons. So change is coming. Another big change factor, China is going to outpace the United States and become percentage-wise globally. We're flipping positions, basically. China is going to take over that market. On the right side of the screen, a couple quotes from Thomas Friedman and his book, Hot, Flat, and Crowded, talks about this global energy crisis, the fact that the world is getting flat social economically, crowded, lots of people, another big change coming. This is the time when we need to invent our way out of this mess. It's an opportunity for this country, and we're taking this very seriously. When we look at office buildings themselves, and all of this will be available, so I'll just flip through it quickly now. Half of the load of a building, we feel, we collectively, the eMERGE Alliance and Universal Electric and those members of the community that support DC, feel that we can positively affect the use of energy in buildings. We can cut over 20% of the load. Data centers is a piece of it. So I said eMERGE Alliance. Who was the eMERGE Alliance? The eMERGE Alliance, and before that there was DC Power Partners, supported by EPRI and Lawrence Berkeley National Lab, that started this initiative back in early 2000, and later joined into the eMERGE Alliance, which is an organization dedicated to utilization of DC. not just supplying it as product here and there, but to actually develop a complete strategy. Room microgrids, building microgrids, distribution grids, moving on out. A lot of great work is going into that. They're looking at the occupied space as a 24-volt DC initiative. 380 volts DC is the global standard for transmitting power to be dropped to 24 for utilization on lights and ventilation and so forth in the space. And that 24 volts is touch safe. 110 in the wall is not touch safe, but 24 volts is. So it's really a very exciting initiative. There's outdoor and indoor opportunities. Who is the eMERGE Alliance? And for those eMERGE Alliance members that are here but not listed, apologize. It's almost a 50% increase of the people, the companies that joined. But please take note, Armstrong, Intel, Johnson Controls, Philips, many government agencies, PNC Bank, a lot of folks saying, wow, this is happening, we need to get part of this. What's even more exciting, or continues to be exciting, there's industry collaboration. Mr. Edison didn't work well with others. Remember the battle with Tesla? Tesla had great ideas. He had the electric motor. Well, Edison couldn't come to partnership with him, but Westinghouse did. Westinghouse understood the value of the motor. Okay? Edison could have changed that. Collaboration is how we're going to get there. Many different government agencies, safety agencies, electric vehicles. How many people understand that inside these new electric vehicles, the fast charging Tier 3 charging system is 380 volts DC? This promotion that's going on for Leaf and the Volt, inside those cars, it's already 380 volts DC. That's because power electronics is comfortable globally at that point. It's not that we came up with that. It came up in a cross collaboration. And our military. There's some bucks going into development. It's going to be all electric ships. All the future ships are all going DC. They're looking closely at 380 versus 400-ish, but it's all settling at a DC environment. Okay, but we're here in a data center discussion. Virtualization, another trend, is driving this to take place. We're taking and condensing applications into smaller footprints, higher power density. The interesting thing from our point is the value of the application. That doesn't change. You're simply doing it in a smaller space. So now you've got more value in that square foot, in that footprint, than you had before. That's simply the point. Reliability is the number one thing in a data center space, and DC power enables us to more cost-effectively produce a more reliable system by the elimination of components and the way that DC actually works. And when we look at data centers, we don't just look at data centers as a rubber stamp, just data center statement. We look at all of the data centers. And from us, most of the people in this room think in terms of data centers over here on the enterprise side, okay? The reality is that's only 0.7% of the data centers in the United States. 0.7% of the actual data centers. 93.3% of them are all those other data centers and wired closets and so forth. EPRI, Lawrence Berkeley Labs, have identified those data centers as those needing the most help to reduce their energy consumption. And power efficiency is a key part of that. The story is pretty simple. Dave Geary, my partner, started this initiative with his partner, Mark Baldwin, back in 2004. Had an idea. I worked for Eaton Corporation for 17 years. I was responsible for watching emerging trends and so forth. Saw their presentation in 2005, and then watched them start and develop the first proof of concept back in 2006. And they managed to start putting these parts together and move it forward. And at that point, we now have the traction, and we'll talk about some of the proof of concepts and where we've developed these ideas from that very rough beginning and moving into better circuit protection and standards.
can see it's time to turn over to the engineering tidbits of the whole idea of DC and for data centers. And it really, to me, starts, at the circuit design level, the electrical engineering design level, and that's what got me excited about this from day one. This is what we've been living with since the beginning of the AC world, is how do we protect AC circuits? Well, as you can see, we have three phases of current and voltage. It's constantly changing. So we've had to provide circuit protection based on a short circuit calculation. We never know what a short circuit's going to look like, so we have to base it on a worst case scenario and apply circuit protection accordingly. So we've been living in a world where our circuit protection has basically been a crapshoot of not knowing exactly what's going to happen when we have a short and applying protection accordingly. This is what we live with the DC world. So right away, to me, this looks like opportunity. We're already working with some major manufacturers on ways to do very fast circuit protection, because we don't have to wait to see what's happening in a system that's constantly changing. You're going to have voltage, you're going to have current. So very fast, we think that we could clear faults and protect circuits and actually protect the circuits at a much better and more precise manner that it's going to be better than AC. We actually did some arc flash comparisons with this that we'll talk about down the road. But we actually are already talking with breaker manufacturers that are looking at this, coming up with new systems, new devices. There's a local one here that we're actually visiting tomorrow to talk about their circuit protection. Very close with Cooper Busman. There's fuses out there today that are rated for this topology that we're using in our proof of concept demos as we speak. Again, we have off-the-shelf high-speed fuses that we could apply to this topology that could never be applied in the AC world. And Cooper Busman's already developed some cube fuses and switches and so forth for PV that now are rated for up to 600 volts DC. So again, things are happening in the industry that they realize that this is coming, so products are hitting the market. Standards and specs. I know that's a lot of concerns out there is, well, what do I follow as far as standards and codes? We actually have a lot of things going on as we speak. Part of the eMERGE Alliance partnership is to have a group that industry can look to develop a technical standard. We're actually writing that standard, and this is the first version of what a comparable Sabima curve would be for the DC as compared to AC, and that's actually evolving and actually turning into a much wider envelope than what the AC world would ever be. Along with this, I now sit on a National Electrical Code DC task group that was just formed, and we are meeting twice a week to go through the National Electrical Code and see what we need to do to come up with language or change verbiage that already exists in the code for that'll be ready for the 2014 next edit to make it more conducive for DC and places to go and look in the code to see how to apply DC. Beyond that, there will actually be new sections of the code written for DC microgrids and other things that are coming as part of this topology. UL and NEMA, they all have special task groups now in process that are looking at the UL and NEMA standards for equipment for this topology. Arc flash, there's being the new arc flash standards that's being written as we speak for IEEE and NFPA. We did an arc flash review that we'll see with Duke Energy, and there will be a table in the arc flash standards now that apply to DC. As well as our partners overseas, IEC is in the process of publishing the first specification that should be hitting the street here soon. And we know our friends in NTT in Japan are applying DC power for their facilities and developing their own specs around 380 volts DC. So we have circuit diagrams that we're developing. We're looking at grounding schemes. We're looking at ways of incorporating alternative energies into the system. This is actually a wiring diagram that I came up with and have shared through our standards groups to see where we're going, how we're getting there, what are we going to do with grounding, how do energy storage are tied to this, how would alternative energies tie to this, and so on and so forth. So that is all underway. This is our concept of what a proof of concept or maybe a first phase deployment would be for a DC data center. We could do it on a row-by-row basis. Have the rectifier and energy storage outside the containment space, feed the overhead busway, which is already rated for up to 600 volts DC, and come out with circuit drops that we've already developed for DC to racks and even in-row cooling. The gentleman before mentioned DC fans that he's interested in using in their data center deployment. Well, EC fan's a DC fan. So we're actually working with the folks developing the in-row cooling and other cooling technologies out there to transition to DC motors. So this is our vision of what our quote-unquote chip-to-grid concept is. It's basically going down to the chip, to the board, to the power supply, to the connector, to the plug strip, to the circuit drop, to the busway, to the rectifier, to the grid. That's as simple as it gets. The loads are DC, we provide DC to the loads. And looking at it from the chip-to-grid concept, we're looking at it from the thing that needs the power, which is the chip, and trying to come up with the best way to accommodate them and that power. And that goes all the way back to the grid. So the story goes back to the power supply. Inside the computer, if you look at a power supply, you have all these different parts that exist in a typical power supply today. The DC version simply removes the first stage rectification and caps. So inherently speaking and talking and working with our partners that develop power supplies, they say, sure, we can make a very efficient AC power supply for a computer. The reality is that I could take that same AC power supply, take components out, make it cheaper, and make it at least 2 to 4% more efficient. So the story starts at the power supply. Oh, that's cool. This is our energy efficiency diagram that you probably see everywhere, that you look at DC power is sort of a similar diagram. But again, it's just taking out components to get to a higher efficiency in the total power chain. There's more and more debate as to how this comparison is being made because the AC guys are saying we can make a very, again, efficient AC system. But the bottom line is the AC system that's going to be very efficient is going to be expensive, and chances are you're going to be running in bypass mode to get close to what we're doing with DC full online systems. That then takes us to inside again the power supply into the rack fans is why not go with DC fans? Right now in the computers and part of the power supply we're feeding fans at 12 volts on the output of the power supply. Again, if we go and feed those fans at 380 volts DC, there's efficiency gains there that we really haven't seen factored into the overall topology and the energy savings with the DC solution. And these fans are actually available as we speak. We have samples and now they're going into production for deployments around the world. So safety, the next thing we had to really look at is the connectors. Well, if there's a weak link anywhere in the system's not going to work. So a big focus was made with a lot of our partners looking at connectors. Anderson Power stepped up to this very nicely and has developed their own connector and have done their own testing and have come up with a touch-safe, latchable connector that will meet UL requirements for make and break with live DC circuits at 380 volts DC. So those are available as we speak and are UL recognized. We also have worked with Delta. They came up with a different concept. Well, and if people are worried about making and breaking connectors to DC power sources and DC power loads, let's make sure that those sources and loads are not energized when we make the connection. So they came up with this PS kill circuit where unless the connections are all made within the power chain to the server, the power supply knows that it can't turn on. And with the short pin that comes with this and disengaging that connector, the power supply will automatically turn off as you're disconnecting the connector also. So some very innovative things that are hitting the market. Another very elegant one is from Fujitsu with the help again of NTT. A very elegant design where you actually have safeties built into the connector circuits with switches and arc quenching devices within for 380 volts DC. So again, new products hitting the market. And from the connectors, we go to PDUs and plug strips. So we've had prototypes of those built, and now there's production on the plug strips and PDUs also. Even to the point of pin and sleeve connectors. IBM's Power 7 mainframe inherently operates on AC or DC. So IBM has worked with Hubble to come up with a pin and sleeve connector that's rated up to 500 volts DC at 30, 60, and 100 amps in the standard IEC 309 configuration that already existed with a clock position for DC. So those are now available also. This is actually a picture of the connection that we used and the cable that was provided by IBM, which is off the shelf for our Duke Energy demonstration and our DC circuit drop with metering built into it for the demonstration that we provided. A couple other engineering tidbits that don't really get talked about. 3-volt DC saves, copper. We had a very interesting conversation last night with a gentleman that said, you know, the resource that really is going to run out first, even before oil becomes an issue? Copper. I never knew that. But this is just a simple calculation of what we can get as far as power out of our standard 400 amp busway at different voltages, AC down to DC. And you can see that we can actually have a more power dense solution with the same amount of copper. A different way of showing that is this. This is, I took that idea and tried to apply it to a 260 kilowatt system and said, well, if I did the 260 kilowatts and tried to compare relative copper size of a conductor, what would it come up with? And this is how it actually turned out. The large blue circle is 48 volt DC. And that's what people think about when they think about DC, a lot of them, is that if you're doing DC, then obviously you're using a lot of copper. Well, they're looking again back at the old telco world at 48 volts DC. The red circle is actually a 208 volt three-phase system. The little blue is a lot of people are looking and exploring the 415 volt AC system. And you can see green, which is the size of the 3-volt DC conductor, sort of tells a story. Copper is less with the 3-volt DC. Circuit balancing, another one of those engineering tidbits. The more we start looking back at going to 415 volts AC, the reality is that all the loads are connected from line to neutral in that system. And load balancing then becomes an issue again. You got single phase loads, hot to neutral. And unless the facility has ways of really keeping track very closely as to how they're balancing or unbalancing the load, they don't realize that there's losses in their systems that they have to realize. You have to derate, or there's capacity losses in the system if you have unbalanced loads. I did sort of a simple calculation, and I said, well, if I have 100% on A and maybe only 90% or 80% on B and C relatively, then basically the total system derating that you're taking with that system is you have to only load it up to 90%, because one phase over 100% will take down your UPS. So again, another one of these little tidbits that don't really get talked about, but in the DC world, you're inherently phase balanced because there are no phases. A few other little tidbits that I'm collecting these as I go, so if anybody knows of any more, I'd love to add them, but little quotes and tidbits that I find as I read some of the technical journals and go back in time and read some of the history documents. But DC power transmission, one thing we all forget about is that AC power is a sine wave. And for a 208 volt system and a 480 volt system, you're not looking at the peak voltage, you're looking at the RMS voltage, the square root of 2. So really, a 480 volt system, the peak-to-peak voltage is well over 600 volts, and the peak-to-peak voltage for 208 is really almost 300 volts. So again, another thing that we sort of lose track of, but that could actually be translated into, if we're using a straight line DC sine wave, we basically can do 1.4 times as much power than an AC line. AC power transmission. AC, you have to worry about reactive losses. In DC, there are no reactive losses. It's strictly resistive losses. DC motors, just the idea of using a DC motor, number one, you gain efficiency, much easier to control. Like the quote here said, it's, starting up a DC motor is by raising the voltage is simply doing an inherent soft start. You change the voltage, you change the speed of the motor. The other thing that I always have been searching for is, well, how does this translate to conductors? Because you can't find anything about wires and conductors. What are the DC ratings? I did find one thing with LAP USA, that basically said if you take an AC conductor, multiply it by 1.5, and that's your DC voltage rating. So again, a little bit of benefit when it comes going from AC to DC. And actually, this is one of the things we're looking to work with UL and NEMA on right away, is that there's things out there that can be very easily rated AC and DC, but they're only rated AC. So now a lot of the manufacturers and the industries are going to look at doing dual rating, so it's more apparent as to what we're dealing with AC versus DC. Our DC rectifier, basically our DC UPS. Again, modular, taking the telco model sort of in mind and do a modular, go as you grow type of configuration. In this scenario, we have 20 kilowatt chunks of drawers that can be added to this all the way up to 280 kilowatts for a rectifier, fully built out with a controller And here's some of the specifications. Also coupled with that configuration could be as many as 4 of these rectifiers with a fully loaded battery configuration. So again, we're seeing products hit the market that are very efficient to go with this topology. And the idea is modularity. Do I have to keep doing that or just automatic? You're the animation master. So basically what we're trying to show is that we're hearing about containerized and modular and so forth. But in reality, this DC concept is inherently modular. You add racks, we add rectifiers. You add racks, we add circuit drops underneath the busway. You don't have to do the full build out of a AC topology with a very large investment day one. You can basically make this grow, the power system grow as your loads grow. Again, so that brings us to the Duke Energy demo. This is the latest demonstration we did, and I basically designed and built this with Duke and EPRI. EPRI's part in this was the third-party validation of coming up with how to meter this, so it's indisputable, the results. We metered every point in the AC system and the DC system. What we did is we provided an HP rack, an IBM Power 7 server, and an EMC rack. And each one of those racks were provided with power supplies, both AC and DC. So what we did is we compared running all these systems on AC and DC at the same time. They work fine. Then we could hot swap switching between AC and DC, and we measured the efficiency difference of the system. This is the picture of the system with the rectifier feeding the overhead busway. I think I have a better picture. With the overhead busway circuit drops, we got the HP rack, the EMC rack, and the IBM Power 7. And EPRI's metered finding is that we picked up 15% of electrical energy savings. That's just electrical without looking at the mechanical. Again, some picture circuit drops and meters of how we tied things together. We had, again, 2 power supplies, AC and DC. We actually had Jim Phillips, who is the world-renowned arc flash expert, come in and do an arc flash evaluation for us and got his opinion on really what is our arc flash exposure to 380 volts DC. He looked at it, he was quite impressed. He said, if you can do fast circuit protection, and maybe even faster than what we're doing in the AC world, your arc flash exposure goes way down. So again, our goal is to make this as safer and safer than the AC, if at all possible. So he actually goes around the world teaching arc flash classes, and he's adding DC arc flash now into his teachings. We also are actually working with Cooper Busman to do a live arc flash testing at the Cooper Busman Short Circuit Lab. And we have him on board with Cooper Busman, so we'll fairly soon, I hope, be able to go and blow some things up. That's the fun part. And get some actual data on really what the arc flash exposure is. Cost comparison. As part of the Duke Energy, we had to show them what our thoughts were cost-wise. So what I did is I tried to build a model of a 2-megawatt system. This is the AC system and the DC. You can see that a few boxes go away when we go to the DC. So I did a simple takeoff of what we thought with the help from contractors and so forth, and the bottom line is we came up with a 15% less CapEx on equipment installation to AC versus DC. And this is actually out of the box today without any volume in the components in the DC world. Once the components hit the market in volume basis, with parts going away, costs are going to go way down, and we think this 15% could balloon to hopefully a larger number. We also did the same things for OpEx, for operational maintenance. Well, how does a DC system compare to AC? Well, since we're modular and since there's less components, and again, our takeoff of comparing actual maintenance cost on their existing AC system and what we would charge on the DC system, there's 35% savings in operational expense. So again, going back to Tim's return on investment. Measurement and verification, this again was what EPRI did with metering, and we worked with meter manufacturers, and they wrote a very extensive measurement and evaluation procedure that we followed. They're still supposed to be coming out with a white paper that explains all this, but they were very instrumental in instrumenting. Sorry. So the white paper really, that's going to come out of this is going to validate the white paper that Intel did a few years ago. Intel did a paper study with Emerson, EYP, Delta involved, and this basically was their conclusion, is that going to DC is 200% more reliable. That's because we're losing components in the system. We've had some people that say this actually could be 1,000% more reliable, depending on where you put a battery in a DC system. You know, all bets are off now with where you need to put your energy storage. If you're on a total DC system and it's on the total power chain, we may have batteries at the rack level itself if we have racks that are more important than other racks. 15% again, electrical facility capital cost savings, we basically verified that. And then the energy savings, again, that's sort of all over the place these days, going from 7 to 8% to over 15%, depending on what you're comparing as far as the AC system goes. So the bottom line is that, especially with Intel being on board, their whole idea and their whole goal was to show that if we do something different, go to DC, we can save energy, the Earth's resources. This is just a picture of some of the other tests and evaluations that have gone on around the world. We've been involved in all the ones in the U.S., but we know France Telecom, Sweden. Again, we know our friends at NTT in Japan, and we know there's things going on in China and other Asian areas also, and in New Zealand. So there's quite a bit of interest. There's finally the opportunity to standardize around the world, and that's a good thing too. So this is, again, the new standard. This is out of Intel's presentation. So again, just again, the value proposition of what we think really are the points that make 380 volts DC the power system of the future. And again, it's not just efficiency gains. And that's it.
Okay.
So any questions, just feel free.
I'd like a couple of clarifications. We're not the only ones doing this, by the way. ABB has announced that they're starting a new division to provide 380 volt DC systems. They've made some acquisitions. We happen to use ABB breakers. So there's AC, they are basically a current neutral company. So it's happening. The AC world says, well, available products. Available products, they mean the IT products, not the safety products. They know those are already out there. Available products. All of the major players in the IT world, IBM, HP, Oracle, Dell, they are all preparing for this. Back at that power factor correction equipment that's taken out, you couldn't see it on the chart because it was so small. That's 380 volts is already in there. So they're already getting ready. So when people start asking, companies start asking to provide DC servers, DC equipment, 380 volts, they're ready to move. So it's happening, and it's happening by request, and we can help facilitate that.